Hello everyone, welcome to this lesson. So in this lesson, we're going to go through the Python code for the golden section search technique. And if you remember, the golden section search technique is used to find optimums, both maximums and minimums. I've also gone through where the technique actually got its name because it's dependent on a famous ratio called the golden ratio. We said that this technique actually mirrors the bracketing techniques because we actually bracket the optimum as well in this particular technique. So the first step, what we do is we bracket the optimum. In this case, we're bracketing the maximum between -2 and 1. And the second step, we're going to get two estimates within this bracket, and we're going to call them x1 and x2. And x1 and x2 depend on the lower limit, the upper limit, and also they depend on a quantity called d. And we have said that d is the golden ratio multiplied by the difference between the upper limit and the lower limit. And once we do this, we actually get the function value at x1 and the function value at x2. And since we're actually dealing with a maximum, we're interested with the x value corresponding with the greatest function value. In other words, here the greatest function value is f of x1, which means the optimum is corresponding to that x1 at 0.146. So what we're going to do is, so after we do that, we actually pick the section in which the optimum is. So the section in which x1 is x2 and the upper limit, and we do the appropriate changes. x2 becomes the lower limit, then x1 becomes x2, then we calculate the new x1 depending on the new d, because if you remember, d depends on the difference between the upper limit and lower limit, and since that change, d will change. So we calculate the new x1 and we do the same thing, get the function value at x1 and x2, and the one that is greatest, the x value corresponding to it will be our optimum. We find that the one that was greatest was x2, and we were still at the optimum 0.146, and we repeated that again. Now, the code for the golden section search is a very, very simple code. So the first thing that we're going to go through, we're going to define the function that we're interested in. Basically, it's 4 minus x squared minus 0.2x cubed. And then we're going, since we're getting initially a maximum, my initial guesses are -2 and 1. So this bracket are the maximum that I have at 0. Here, so these are a few initializations. This is the header for the information that we're going to output later. We're initializing the EA at 100, and also the number of applications. We're going to start I at 1. Here we're going to be creating all the initial values for these values here. We're going to get the golden ratio as the root 5, so 5 to the power of 0.5 minus 1 divided by 2. And given that I have r and the upper lower limit, I can now calculate d for my first iteration. And given I have d and upper lower limit, I can now get x1 and x2. And given I have x1 and x2, I can get the function values at f1 and f2. So basically, we have calculated everything for the first iteration here. So now we're going to be doing what we did here, which is basically compare the function values. So we're going to say if the function value at x1 is greater than the function value at x2, we're going to do these changes in the numbers. So if you remember here, the function value at x1, which was greater than the function value of x2, what did we do? So x2 became our lower limit, right? So basically, the lower limit xl is equal to x2, so that's the first change that we did. The second change that we did as well is that x1 became x2. So here you're going to find that x2 is now equal to x1. And now given that we have switched those, if x1 is now equal to x2, f1 is also equal to f2. So we're going to do that appropriate change as well. And also we said that given in here we had the lower limit x2 and the upper limit, now we calculate x1 based on the equation that we have here. And basically x1 is the lower limit plus the golden ratio multiplied by the new upper and lower limit difference that we have here. And given that I have x1, now I can get the corresponding f1 as well, right? So this is basically if the function value at f1 is greater than the function value at f2. So if that's not the case and f2 is greater than f1, I want to do those appropriate changes down here. And this is mirrors basically what we have in the second iteration here. So the second iteration, f2 was greater than f1, and what we did when that occurred is basically x1 here became our upper limit. So if you go down here, the upper limit is now equal to x1. And also another appropriate change is that x2 became x1. So you see here, x1 is now equal to x2. And of course, if x1 is equal to x2, f1 is also equal to f2. So we switch these. So we store x2 and f2 in x1 and f1. And given that I have the upper limit and given that I have x1, now I need x2. So I know from the equation up here that x2 is equal to the upper limit minus the ratio, the golden ratio multiplied by that new difference between the upper and lower limits. And given that I have x2, now I can get the corresponding f2. So basically we have put into this f statement all the changes that we have done with the second iteration and all the changes that we have done with the third iteration here. So let's see. So given that I actually did these appropriate changes, let's actually figure out where the optimum is. If f1 is greater than f2, and since in this case we're actually getting a maximum, then the x optimum is corresponding to x1. And else, if that is not true, that means f2 is greater than f1. That means x2 is our optimum. Again, we're only dealing with a maximum now. And that's going to be slightly changed as we go to dealing with minimums. Given that I have my new estimate now for x optimum, now I'm going to get the approximate error for the new iteration. And we said that this is the new equation that we dealt with here. Is 1 minus the golden ratio multiplied by the absolute value of the difference between xu and xl divided by x optimum multiplied by 100, since again we're dealing with a percent. This is a print function because I want to know for each iteration what is my approximate error and also what is my x optimum. And this just increases the number of applications as I go along. So let's actually begin. So again, we're dealing with this function. We're dealing with an initial guesses -2 to 1. So we're bracketing the maximum. And here we're doing it for an approximate error of 0.01. So let's actually run this. Okay. So here we're basically, we had 53 different iterations. We went below 0.01 and we can see we actually reached the maximum at 0. Now the reason we're dealing with so many iterations, and also if you look at the approximate error, is kind of all over the place. And also if you look here, we get stuck at, like here we got stuck twice for this number, 4 times at this number, 4 times at this number. And that usually happens if you're dealing with an optimum both at 0, because the maximum is at 0, and also the derivative is at 0. So this is usually happens when you are dealing with this type of optimum. We're going to see that when we're dealing with a minimum, that's not going to be the case, and it's going to converge in a much more seamless, much more continuous way instead of this erratic nature. So that's actually, given that we have dealt with the maximum here at 0, let's actually do with the minimum. So the minimum, let's actually bracket it between, say, -4 and bracket it between, say, -2, since our minimum is at -3.33. And the next change that we're going to be doing is, instead of dealing with f1 greater than f2, we're going to be doing basically less than, since we're dealing with a minimum. So if I run this, I should expect to get the minimum at -3.33. So if you see here, I have -3.33. So much like I told you here, you can see that it naturally converges to the optimum at -3.33 in just 12 different iterations, as opposed to the erratic nature of getting an optimum around 0. So here just took 12 different iterations. Now, given that we have dealt with getting the maximum at 0 and the minimum at -3.33, I want to show you a trick that you can actually get both the maximum and minimums by just a change in sign. Now here you can see that the upper limit and lower limit, we have bracketed it exclusively. So we bracketed the maximum first, then we bracketed the minimum. What we can do is we can actually pick a range that brackets both. So I'm going to say from -4 to 1 is it's a section that has both my maximum and minimum. So what I can do is, depending on how I play with these signs, greater than or equal to, will depend on whether I get a minimum or whether I get a maximum. So let's actually run this. So since this is less than here and this is less than here, I should expect to get a minimum. So you can see here, again, 14 different iterations at -3.33. So let's actually change this sign to a greater than and run this, and if this actually holds true, I should get the maximum at 0. And you can see here I got my maximum at 0. So the great thing about this code is that you can just bracket once. You can pick an upper limit or lower limit that brackets all your optimums, and depending on basically whether you use a greater than sign in here in this F statement and this F statement, or a less than, will depend whether you're converging into a maximum or converging into a minimum. It's a pretty neat trick that really all you need to do with this code is just change signs to converge to whatever optimum that you're interested in. So to kind of recap, we dealt with, in this lesson, we developed the Python code for the golden section search, and it again mirrors the bracketing methods, where the first step, we bracket the root using 2 values, then we get the 2 values within that using x1 and x2, which depends on d, and d depends on the golden ratio and the difference between the upper and lower limit. And once we do that, we identify the function, we analyze the function values. Again, if you're dealing with a maximum, we see which one is greater than the other, and the one that is greater than the x value correspond to a maximum. And if we're basically comparing them, which one is less than the other, we're converging towards a minimum. And I also showed you that showed you an example of converging into just the maximum and converging into just the minimum, and also showed you how you can just use a generalized section that houses both, and we're just a change in sign, you decide which one you want to converge to. So that's it for this lesson, and I will see you in the next lecture. Thank you very much.